Hello everyone, and welcome to this lecture of machine intelligence. I'm Alba, and today we'll explore one of the most important concepts in machine learning, regularization. We'll see how it helps our models stay balanced, accurate, and reliable. By the end of this lecture, you'll be able to explain underfitting and overfitting, understand how regularization controls model complexity, distinguish between ridge and lasso regularization, and interpret the bias-variance trade-off visually and conceptually. Let's start with a simple idea. A model that's too simple can't capture the structure in data. That's underfitting. But a model that's too flexible starts memorizing the noise. That's overfitting. Our goal is to find the balance between the two. Now, imagine fitting a straight line through curved data points. It just doesn't work, and that's underfitting. If you instead use a very high-degree curve that passes through every point, you'll get a perfect fit on training data, but poor predictions on new data. The best models capture the main trend while ignoring random noise. Training error usually decreases as models become more complex, but validation error behaves differently. It first goes down, then rises again. The lowest point of the validation curve represents the best generalization, the model that's just right. Simple models make consistent mistakes, or that's bias. Complex models fit the training data well, but vary too much with new data. That's variance. The trick is to stop adding complexity when variance starts to dominate, keeping the model general but accurate. To prevent overfitting, we add a penalty to the learning process. This penalty discourages the model from relying too heavily on large parameter values. It's like a soft brake that keeps the model smooth and stable without limiting its ability to learn. Regularization is like teaching the model self-control. When the penalty is small, the model can bend freely to fit data. When it's large, the model becomes simpler and smoother. Our task is to find a value that balances accuracy with simplicity. In ridge regularization, we add a penalty based on the squared size of the model's parameters. This gently shrinks all coefficients towards zero, but never completely eliminates them. It's especially useful when features overlap or are noisy. Think of each weight in the model as being attached to zero by an elastic band. The stronger the regularization, the tighter the band pulls. The result is a model that's stable, smooth, and less sensitive to random noise in the data. Lasso regularization works differently. Instead of reducing every weight slightly, it forces some of them to become exactly zero. This makes the model simpler and automatically selects only the most important features. Lasso is like pruning a tree. It removes weak branches and keeps only the strongest ones. As we increase the penalty, the model becomes smaller, easier to interpret, and often more powerful for prediction. The regularization parameter lambda decides how strong the penalty is. A very small lambda means almost no regularization and the model might overfit. A large lambda oversimplifies the model. We usually tune this value using validation data. Choosing lambda is like tuning a dial for simplicity. Start small and gradually increase it until the model becomes too rigid. The best point lies in the middle, where both bias and variance are balanced and the model performs best on unseen data. To sum up, regularization is about balance. Ridge regression smoothly shrinks all parameters, while lasso drives some of them exactly to zero. By tuning lambda correctly, we can achieve models that generalize better, perform reliably, and stay interpretable.